I've been in water technology now for 7, 8 years, something of the sort. Started as an outside rep and worked with a company that was altering the properties of water, if you can believe that. And so I started there, and then I found, well, rather PAX found me and brought me in to help build their organization and sales. Our company is based out of this area. I now live in Denver, mostly so that I can get around my region. And I'm a big fly fisherman, so moving to Denver, convincing me was pretty easy to do. Marijuana only had a little bit to do with it. That's right. No, I totally understand.
Well, say cool, man.
So, our company is located here in the Bay. We're the red dot, and the reason that this is of any significance is we are in the mecca, if you will, of technology. You have the Silicon Valley just down here, and these two yellow dots are our partnerships. We have a strategic partnership with Stanford University and with UC Berkeley. The company is run by a Berkeley grad, and we have multiple Stanford grads. What that means, it's not just a fancy title, is that we have access to all of their equipment, things that we could never buy. CFD modelers and supercomputers. If you all know who's heard of CFD modeling? Okay, stands for computational fluid dynamics. In other words, what it is, it's a way to model what's going to happen in different fluids and other properties prior to it actually ever happening. So if you want to see the way that water moves around the inside of a tank, you can actually model it given a set number of parameters, and it will show you a three-dimensional picture of the way the water is moving inside your tank, relatively accurately. And with that, we're able to develop different technologies. We can make something that makes water spin around and so on and so forth, and we know what's going to happen before we invest millions of dollars into producing it. So that's a little bit about our company, and I think it took less than 5 minutes. So we'll move on. Goal is that everybody learns something new, okay? As if knowing that Nate Miller works for PAX and now lives in Denver, where pot is legal, is not something new enough. So what we're going to talk about, obviously, like the title said, we're going to talk about distribution and water storage tanks. We don't, as a company and in general, we don't play around in this arena, in treatment. And what's interesting is if you look at the dollars spent every year, 90% of proactive spending, I'm not saying reactive, chasing broken pipes and things of that sort, proactive spending is actually done in the treatment plant. Then what happens to the water? It goes out into distribution, but no one touches it once it's in distribution. The water is going to be as good as it ever gets leaving this treatment plant, and then you send it out on its own and hope for the best. And the whole time you're out there sampling different places and this and that, and you're not managing water, you're watching it decline. So what we did as a company, and what we're going to focus on, is distribution. There's very little money proactively spent in distribution, although that's where water spends all of its time before it goes out to the general public who drinks it and pays for it. Make sense? So what is driving mixing? Who in here has heard of mixing in your water towers and tanks? Right. So it's not something that's brand new, but it was pretty much brand new 7 years ago. Well, what's driving it is EPA regulations. Who's familiar with stage 2 compliance? A couple of you? Okay. Who's got a water system that serves less than 10,000 taps? All right. So your rollout of stage 2 is just around the corner if you haven't already gone through it. And we'll go through what that means real quick. Currently, if you're not under stage 2 guidelines, you're under stage 1. Stage 1 was this averaging of all of your system sample points. So you have some areas where you test your water and the water's not so good. Maybe some elevated DBPs, things of that sort. Then you have some areas where the water is great. And under stage 1, what you would basically do is take your good water report cards, if you will, average them with your poor water report cards, and that's your grade, your passing grade. So you can skate by with a C average, okay? I don't imagine that there's anybody in here that has ever skated through school with a C average. I did. Under stage 2 compliance, it's a little bit different. EPA says, okay, well, we know what you're doing with your C averages, and we want everybody to be an A player. So they're going to say, well, we're not going to look at your good sample points anymore. We don't care about that. We're going to help you to identify the places where your water is the oldest and you have the most problems. And then we're going to make you report on that each quarter as an individual sample point. So you see how that kind of elevates things? It makes it a little bit more difficult to get straight A's. So that's what stage 2 is doing. And the reason mixing is important is because in that, water travels through water storage tanks. That's where a lot of water age occurs. That's where a lot of water problems occur. Now, under this whole guideline, there's this thing called the EPA Guideline Disinfectant Manual, so on and so forth. It is 600 and some odd pages of fantabulous reading produced by our tax dollars. So if you haven't picked up a hot copy, get it now. In here, there's a couple of key points. One of them, I highlighted for you. Higher temperatures increase the reaction rate of DBP formation. Who knows what a DBP is? Okay. We'll get into that in a little bit, and that's where the cartoons come in. Therefore, warmer water temperatures result in higher levels of TTHMs, HAA5s, which I know are not very prevalent in this region, but nonetheless, they're a byproduct of disinfecting water. Unless better removal of precursors is achieved during treatment. Well, right there, that's kind of shenanigans. You can remove a whole bunch of organics and have great water coming out of your system, but once it gets out into your distribution system, it can continue to build organics. There's all kinds of places in your system where contaminants can get in. Your water storage tanks is one of them. So in this manual, it's got a couple of suggestions in terms of how to better your water quality. One of them, improve tank mixing and turnover. Good for the EPA. Good job, guys. But one of the things in here that I don't agree with is it says eliminate access storage. Access storage. That sounds to me like fire protection. So an engineer designs a water storage, you have too much capacity, let's eliminate it. Well, the reason it was designed is to have capacity in the case of an emergency. Who recalls a pipeline that blew out of the ground in California up towards San Francisco about 3 years ago? Okay? What happened in this particular municipality is they were keeping all their tanks at half capacity. They're a chloraminated system. Anyone in here on chloramines? Ammonia and chlorine? Okay. So they're a chloraminated system. Well, with chloramines, if water sits idle long enough, then it starts to lose disinfectant properties and the ratios get out of balance. You can get nitrification, all kinds of bad things. So their solution was to superimpose demand by lowering the water level in their tanks. A pretty common practice. Well, the thing about catastrophes and disasters is a lot of times you don't see them coming. If you could see them coming and avoid them, they would probably not be a catastrophe nor a disaster. So this gas pipeline, PG&E, blew out of the ground, lit on fire, torched about 4 blocks in, down just south of San Francisco, where the average home price is about $980,000. And the average lot is only, 10 feet by 10 feet. So it burnt a lot of houses. Now, the significance of this, not only the whole catastrophe thing, so on and so forth, is that the operator was on, or the chief of police was, fire rather, was on TV, and he was being interviewed. And they asked him, what could have been done to mitigate these, all the places burning and everything else. Well, the chief said, had they had adequate water storage, in other words, had the operator not been at half capacity, he could have saved 2 blocks. That equates to, like $80 jillion in San Francisco. I mean, that's huge. So in terms of the operator's responsibility in this, the chief basically came out and said, it's your fault. No good. So 2 weeks ago was the Colorado Rural Water. And I went and I presented there, and I talked. And anybody that came around our booth, I asked them this one simple question. How do you operate your system in the winter, meaning their distribution? Of 20 people, 20 actual operators that came by, 60% of them said that they lower their winter tank volume. I said, interesting. Why do you do that? Well, ice is number one. They're getting ice damage, lower it so that way that they can cycle their tanks, and they're all groundwater systems, so it helps the ice. The other one was an attempt at mixing. Superimposed demand. People use less water in some neighborhoods in the wintertime. Sprinklers aren't on, so on and so forth. So right there, I knew that in terms of the 20 people that I talked to, 60% of them were not ready for some sort of disaster in their neighborhood. I just thought that was an interesting little statistic. So let's get on to the meat and potatoes, the learning portion now that I've scared y'all. Okay. There's 3 elements of stratification. Okay? And we're going to talk about stratification in terms of water quality. Who knows what stratification is? How many people in here fish? Have ever fished? We're in Minnesota and you're not all raising your hands. That's what happened. So stratification in terms of fishing, you guys all understand how that works. Number 1, you need a heat source. The sun, that's pretty constant. I hope it's around as long as I'm around. Heat sink. Well, we have water storage tanks. Not many of them are as colorfully painted as this, but that's a real tank down in Georgia, poor color choice. And then the third, you need physics. Physics is a natural. So the sun heats the tank absorbs the heat, tank transfers via physics the energy into the water. Now that's an important thing. It's not about how hot the climate is. It's about how intense the sun is and for how long the energy is transferred. And I'll show you guys in a bit. So just in terms of stratification, this is kind of what it looks like. The beginning of spring, we're going to be coming into spring here. Most of your tanks probably look like this or have some ice floating in them. Not much stratification. Water temperature is all the same. Well, coming into spring, the days get longer. More thermal radiation starts to push down onto your tank, and the energy is dissipated into the water. So you might get a little bit of stratification starting to form. It only takes about a degree and a half to start really forming stratification. When it sets in, it's a boundary. So you have 1 day old water, maybe April 1st, okay? First warm day or series of warm days, longer days, and you start getting a little bit. So this stratification keeps going. It doesn't stop during the summertime. Maybe you flush your tanks or something of that sort, but it can reoccur real quick. Well, if you're 3 weeks into your first stratification episode, now you've got 3-week-old water. And maybe you let it go all summer. No one ever climbs the tank to do any kind of grab samples, temperature samples, something of that sort. And so you have old water sitting up there. Most people don't know that they've got old water. Until something like this happens. This is a picture from a water storage tank. That is taken from the hatch, looking down on the water. If it is, I wouldn't admit it. I think that's illegal. But this bird floating around on top of the water storage tank, now this is down in Texas. The operator never picked this up in his grab samples. You know why it never picked it up on the grab samples? Because the water is stratified, and he's only sampling good water from the treatment plant. There is no floating grab sample that samples the top of the water. Okay? So that's the risk that you run. And then what happens as a fisherman in the fall? What happens to lakes and ponds? Right. So they turn over. Now, what's really interesting is when I go around with reps and we chat, we'll go and talk to a bunch of municipalities. And what I try to teach the reps to do is ask operators, what happens in the fall? Because almost all operators, if you ask them, how's your water quality? Oh, it's great. Do you ever notice anything off in the fall? And they'll say, well, during the fall, somewhere in and around, October, November, we'll start to see a little dip in residual, or we'll get a taste and odor complaint or two for a short amount of time. The reason that is that this bad water that was up here flipped over, went into distribution, and now customers are picking it up as it travels down through the system. Once it passes through, it's gone. But who knows what you just sent down to your customers? So that's the risk that as operators you have to manage. And an example of what I was just saying in terms of that outside temperature, this is a stratification study. Temperature probes inside of the tank. Okay, they're logging the top of the water, they're logging the bottom of the water. There's this large difference in temperature from top to bottom, strong stratification. This is in Maine on the coast. Maine is pretty cool all year round, even in the summertime. It hardly ever gets real hot. And so this just goes to show that stratification can happen anywhere. And I've probably got 150 of these examples. Even Canada, lots of Canada. So let's look at the source water and how that affects it, okay? How many people are groundwater in here? How many people are surface water? Okay. So groundwater, you're at a disadvantage in terms of stratification. You've got cold water coming into a water storage tank from underground. It's a constant. And it rises up into a body of water, your water storage tanks, that's been energized, that's collecting heat from the sun. So right there, it's instantly coming into an atmosphere for stratification. I'm not saying every single one of your tanks is stratified, but I'm saying that the conditions are there to make that happen. Conversely, if you're a surface water person, stratification, it's relatively rare. The downside to surface water systems is organics. There's far fewer organics in groundwater applications than surface. So in a surface water application, you might get a degree or two of change, but the real problem there in the summertime is that you're creating this tropical oasis inside your tank. A tropical oasis in which biofilm can grow. Who's heard of biofilm? Yeah, biofilm. So biofilm by itself is not a bad thing, and we'll talk about that here in a minute too. So you can see the two different situations. Groundwater, yeah, you can get some stratification, but the organics aren't there and you might not have as much biofilm. However, you still have stratifying your water. And then surface water is kind of the opposite. Higher organics, higher bacteria count, and there's more risk in that. So biofilm. This is a tank in Southern California. That little bucket there is, and this is an underground tank, it's in the ground. This little bucket is what they use to disinfect this tank, to bring the residuals back up. They send somebody out there once a week, he puts a little bit of chemical in there and he sprinkles it all around. And that's their way of trying to keep their residuals up. The real problem is that they're not losing residuals per se in the tank just because it's old. The real problem is floating on here, on the surface. Every time they take this little bucket and sprinkle the residual in there, two things are happening. One, they're wasting labor and time, and two, they're creating DPPs, disinfectant byproducts. We'll talk about that here in just about a second. So, biofilm, like I just said, is not bad in itself. Even though you've all heard it, and you'll hear some people talk and say, oh, biofilm's terrible, watch out for biofilm. It's not the biofilm that's bad. Biofilm is in every one of your tanks. Every single tank. You can never eliminate all the organics and naturally occurring matter in your water system. So biofilm will always be present. The problem with biofilm is that it forms this skin, this exopolymer, if you will, polysaccharide slime. Just like on your showers and whatnot, if you haven't washed them for a while, they get kind of slick. That's the slime, and behind that is where bacteria lives. The slime is secreted so they can protect themselves against things like residual. There's another picture. This is, I think it's an Ohio tank. And once again, the operators never saw, you don't see a change in your water quality with this floating on the surface because your sample taps are sampling water from the bottom. So biofilm and DVP formation, okay? I told you it's going to get a little basic, but trust me, it'll help. So this is my explanation of what a DVP is. You have residual, and you have organics. Organics are always present. When a residual and organic run into each other, and the residual does its job, and it kills whatever kind of organic is in there, disinfects it, something out of that forms, right? There's a byproduct. And so that becomes a DVP. That's the goal of residual. That's what it's there for. Now, in a tank that's poorly mixed, or it's not getting the right turnover that it needs, and it's not homogeneous, organics in your system will start to build up in the warmer water. It's not rocket science. If you take a warm body of anything, of water, and you lower the water level, the sides of the tank stay wet. So it's getting air, and it's nice and warm, and there's organics in there. That's the kind of environment that mold likes and that organics like and need to grow. And then the water level comes back up, and it gets wet again, so they're getting everything they need and they're protected. Under that scenario, that's when you start to see the floaties, like I just showed you a few pictures back, of the biofilm spreading across the surface. And that's the same scenario here. Stratified tank, they go and checked, the disinfectant is not doing its job, or able to mix into that upper level, and they grow across the top. Now DBPs start to elevate, or if you're a chlorinated system, you might have issues with controlling your nitrification, because you've got this water that's coming in that's rich in chlorine, or if you're a chlorinated system, ammonia, you're introducing food to these organics basically. And what's happening is this high density of organics meeting this high density of residual are forming a mini war inside your tank, resulting in a high level of DBPs, or nitrification events. If you mix your tank, you don't give them a chance to grow and bloom to that large scale. You'll always have some organics in there, and that's what the residual is there for, okay? But you'll never, if you have good water circulating through here the whole time, then you've always got good residual coming in, getting to all the corners of the tank. Everybody with me so far? Got it. So, and in here, I mean, I put this down here. So there's a key. As operators and people working out in the field, look out for drops in residual for no good reason. A lot of times it's because there's something organic that's blooming that's eating up your residual. And then the other thing, obviously, if you're a chloraminated system, watch for issues regarding your break point, your chlorine and your ammonia ratios. If those start to get wacky, then it's a good chance you can go look at your tank, you might have some bacterial issues. So what are some other byproducts of biofilm? Well, elevated DBPs, which I don't see a lot of here. Not as many as, say, Ohio. Ohio's got a lot of trihalomethane issues, but that's associated with their surface water and their source water. Residual issues, obviously, nitrification, taste and odor is a big one. So if you're getting a lot of taste and odor complaints, don't automatically think it's your well. Have somebody take a look at the tank. And then bacterial failures. E. coli, everything you're supposed to test for can be protected by polysaccharide slime inside water storage tanks, and it can make it out into the system. So those are all byproducts of biofilm. Biofilm itself is not bad. So there's stratification and hydraulic workarounds, we like to call them, mostly designed by engineers. And I get drawings like this, probably starting to slow down, but probably 2 or 3 drawings a week, asking various questions about turnover, volume, so on and so forth, and whether or not elevating their inlet up here on this particular hydropillar would help them with mixing. And I'm honest with them, sometimes it will help them and go on their merry way, but sometimes not. So the current design for tanks, and it's actually mandated in most states, is a separate inlet and outlet. Water comes in, needs to go out some other way. And the idea behind that is for mixing, obviously. So water comes in one side, it's cold, it's dense, especially groundwater systems. Colder water is more dense, it sits along the bottom, it bounces along the bottom, and it goes out the other side. And then some people have elevated inlets. I see this quite a bit. Or they have a passive mixing system. Cold water comes in, and then obviously it's cold, it falls to the bottom. This scenario will never work and fully mix a tank, ever, unless your fill cycle is 24 hours a day, in which case it's hardly a water storage tank, it's more like a pipe. This particular tank is another example of stratification. The reason this is in here is, I know you guys can't see it in the far back, and it's really hard to see it through your eyelids, but this is just making sure you're awake. But from August 10th to August 14th, 4 days is the time span, okay? In 4 days, you're looking at the 1 degree rise in the surface water over the bottom of the tank in terms of temperature and water temperature. This is significant because one of the things I hear all the time is we flush our tanks. How often do you flush your tanks? Oh, when it needs it. How do you know when you need it? Oh, well, we're on a program. You know, it goes on and on. So if you're not flushing your tank, I'd say every 3 days, every 4 days, every week, then you're really not getting representative samples because there's a good chance that your tank is stratified. So that's why I'm relatively anti-flushing tanks. There are some tanks that I do think that helps. And then the last issue, ice formation. You guys have a little bit of ice here. Polar vortex really gave it to you this year. Did you guys notice that there was a winter storm called Pax? I bet you guys didn't know, obviously. But, see, now you learned something today. Yeah, we did it good to the East Coast. Gave it to it. All right, so ice formation. This is not rocket science either. That's what I love about this job, is that this is really not that hard. So ice forms inside your water storage tanks. How many standpipes in here? How many people have standpipes? Pretty common. Pretty easy way to get pressure. Nightmare in terms of water age. If you actually do a water age study on your standpipe, it's a nightmare. And in terms of ice, it's pretty bad too. Obviously, you all know how ice works. Things get cold, they start to freeze. And you get this little plaque, this little layer of ice on top of your tank. And it starts to form on your sidewalls. And so it starts to get thicker on the sidewalls because they're in contact with the tank's in contact with the outside air. Remember that whole physics thing? That's where it freezes. And you start building up these layers. And sometimes the top gets thicker and thicker. One thing that you might want to think about is your telemetry. Now your tank might tell you that you've got, 750,000 gallons of water. But I doubt many of you know exactly how thick the ice is inside your tank in the wintertime, if you have ice. And if you take that into account, that would mean that your telemetry is off. And if you're keeping your tank at half capacity to try to be able to force turnover during the wintertime or reduce ice, but there's still ice in there, then you've got actually half of what you think you have, which could be problematic. So it's something to think about. And then the worst case scenario, mainline breaks in the wintertime. That can cause some serious issue to storage tanks. Most of them ground storage tanks and elevated tanks. But if there's a disaster and say you break your main line, water rushes out and you create this void, and if this gap up here is strong enough and bridge is hard enough to seal everything off, now you've created an area of suction. That suction will pull in the top and also pull in the top of your tank. And this is relatively common. I mean, there's probably 15 of these a year somewhere in America. And there was actually a pretty good one this year. It was an elevated tank that collapsed, and the jostling of the collapse forced the whole thing to fall over. In the wintertime, at night, when it hit the ground, the rest of the water splashed against the house and tore the whole side of the house off. That one was pretty impressive. That was Indiana. But, I mean, they're not all that bad. 15 a year, you know how many tanks are out there? The odds are pretty low, right? But little things like this. Number one, the coating. You guys pay a lot of money to coat the inside of your tanks. Imagine if you coated your tank this last year, ice came in, and it tore up the inside of your tank. That causes bacteriological issues. The reason that you coat your tank, other than to protect the steel, is it also seals up all the larger pores, and it makes it harder for bacteria to wedge its way in there and grow. Then you can get little punctures, holes inside your tank. When ice falls down on the inside of the tank, when it presses out, you know, you guys get it. Glaciers, and glaciers are pretty strong. Same idea inside here. Then ice rings. Anybody with elevated tanks has some sort of substructure inside their tank that helps keep everything rounded in place. When ice grabs a hold of it and starts moving it around, bad things happen. Then you also get exterior punctures pushing out the side and costing you a little bit in terms of repairs and so forth. Sometimes they tear up other mixing systems, passive mixing systems if they're inside tanks. That's in Pennsylvania this last year. And then who knows what this color is other than chocolate milk? Those are the shavings. That used to be the interior coating. So they took their tank down to have it recoated, knowing that ice had been in there, and all this little coloring in here, you know, the brown and everything else. So the brown is part rust from the exposed steel from the ice, and the white bits, that used to be the coating that they probably paid, whatever, $100,000 to have done 10 years ago. So it's kind of throwing away money. And then they got a custom design on their ladder via ice. And the surprising thing is that the ladder's still on there. One of our partners, almost always in freezing climates, if they don't have a mixing system, they get rid of the ladder. Because as soon as ice gets in there and tears it up, now it's unsafe to climb on. It's useless. So, that's a little bit about ice. Now we'll get to the fun part, technology. Who likes technology? Yeah, I'm with the other ones. I hate it. It's terrible. So obviously, technology always changes, and it seems like the race is always to make something smaller, faster, whatever it is, more powerful. I mean, look at cell phones. 15 years ago, you couldn't carry around a computer with you. 20 years ago, you couldn't carry around a computer with you, let alone have a cell phone. And now we have a computer inside a cell phone that does all these things, and you know, you can monitor your house from it. And some of you are wired into SCADA, can operate your system with your cell phone, and that's pretty sweet. Well, it's kind of the same thing that is happening in terms of technology. So in 1995, that was when mixing first became a thing in water storage tanks, and it was built around passive mixing systems. So this tall thing here, these are flappers, and the way this works is this is connected to your inlet. Water coming in through your inlet goes up through the pipes, it builds up pressure, and then these, given the pressure, squirt the water out at a higher velocity. Which I'll tell you is not a bad technology. I mean, you wouldn't expect that from somebody that doesn't sell that technology, but it's not a bad technology. It makes a lot of sense. It won't work in tanks that are low turnover because it takes the inlet pressure and the constant filling to be able to mix, but it's a viable technology. And then in 2000, because there were tanks with low turnover being 20% of volume per day or less, active mixing came on the scene. And the active mixing system was relatively large at the time, and it floated and it went down to the bottom, sucked water off the bottom, then made it over to the top, and away you went. And then in 2005, that's when our company started mixing in water technology. This was our first mixer. Our goal was to make a really small mixer that mixed large volumes of water. And then this last year, we came out with an even smaller mixer. And so it just kind of shows the evolution of mixing. And likewise, other mixing companies also have smaller mixers. So what to consider when mixing? Well, the number one thing, you know, when people call our office and say, I want a price on mixing, on a mixer. Why? That's what I always ask them. What's your goal? Well, maybe it's stratification. Maybe it's helping with blending so you reduce your nitrification events. Maybe it's reducing DBPs. Maybe it's removing or eliminating TTHMs in distribution, which, if anybody ever tells you mixing alone can remove trihalomethanes, they're just wrong. That's not how you get rid of trihalomethanes. Just want to be clear. So if you ever hear that, run away from them, pick up the phone and call me, and we'll have a conversation. And then maybe it's ice prevention. Maybe you want a mixer for ice prevention. Well, there's a lot that goes into that. It's not just, okay, well, you want one for ice prevention? Here's some technology. There's a lot of different caveats to it. What size is your tank? What volume? How much turnover do you have? Blah, 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 blah. Which is why turnover is so important when choosing mixing technology. Your percent of daily turnover will dictate what size and how powerful a mixer. In other words, how quickly an active mixer will turn your tank over in place of regular daily demand. And so 5% turnover of your total volume, a 1 million gallon tank, 5% turnover is a very small volume. you have a long time to play with that water before it goes into distribution. So you can get away with a less efficient mixer, we'll say. But if you have a tank that has 20% turnover or more, and you still have ice or stratification issues, things of that sort, well, now you have a smaller window to mix and blend the water that's coming in before it goes back out to distribution. And depending on what your telemetry set points are, so on and so forth, that window can be as small as 5 hours. And so what we believe is that you should never have a turnover less than 6 hours per day in terms of blend time and mixing. Reason being that allows you 4 complete blends per day, and it takes all the guesswork out of your fill cycle and your telemetry and everything else. You don't have to play with your telemetry and get good mixing under that circumstance. And then 3, the third thing to take into consideration, credible design and support data, scientific data, not made up or anecdotal information, or quote, Mike from so and so municipality says he bought one and he loves it. I mean, what? That's nothing. That's out of context. But actual data, and by that I mean independent. Underline independent, not in-house. Somebody else does it. CFD, saying what the mixer is going to do and how much volume and so forth is it going to produce. This is a Stanford Labs CFD. Field data. Something to verify that this make-believe volume mixing thing is accurate. Do they go into the field, do they collect data, and does it match what the computer says it's going to do? And then how do they calibrate the two? So field data. And then the last one, logic. If somebody tells you something that sounds too good to be true, it usually is. Okay? So, that's my little spiel about mixers. Now let's look at some case studies. First one, Atwater, Minnesota. So this last year they put in a mixer, this last winter. Small tank, 100,000 gallon elevated tank, history of ice accumulation, and at the week of this case study, the average temperature was about 0 degrees. Pretty warm, yeah. So this picture here was taken January 2013, so last January, and we needed something to compare it to. So that was this time, or January 2013, and I don't think it was as cold that winter as it was this winter. This winter, in late December, this is the one that we put a mixer in. There's a drastic difference. And yes, we know it needs to be repainted. But there's a drastic difference between the two and destroying the coatings.
Same level, not just
As far as I know. Is the operator from Atwater in here? Yeah?
They just got done painting it.
Oh, okay, good.
Good. I think you said it needs to be painted.
Oh.
Oh.
What was is the operating level the same?
Yeah.
Yeah.
It's 2 foot higher this year.
2 foot higher this year?
Yeah.
Then this is another case study. So this is Ming. Now this is one that we publicize a lot because it's interesting. It's 2 different tanks right next to each other, side by side. Now the reason that mixers were even considered, this was a few years ago, was because this tank right here formed a bunch of ice in it and it had a partial collapse, so they had to rebuild that portion of it. So they said, okay, we got to do something about this. Boilers, nah, too much energy, blah, 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 blah. So we convinced them to let us put a mixer in it. This was the old school ones. And then we bought this fancy technology. We bought an infrared camera, which is pretty fun to play with. There's nothing like getting a bunch of science dorks together and giving them technology like this, I'll tell you. Wild time. So these are the 2 tanks side by side. So there's no change in the operation of them. This one has a mixer in it, this one does not. You can see their groundwater system. The one without a mixer in it, you can see the warm water sits at the bottom. Water comes in, it sits there, and it goes back out. This is the one with the mixer in it. Now this is not a 3-dimensional camera. That would be even neater. But what this shows is the outside skin, the temperature on the outside skin of the tank. What these red lines are showing is return water. So the mixer sits at the bottom, it pushes it up, and then the water returns along the walls coming back down. That's warmer water coming along the walls, coming back down, and that's what's being picked up. So it was really neat in terms of scientific evidence of what's going on inside the tank. This was in February of '09. This is the one with the mixer, and this is the one without. No company should say that mixers eliminate ice. They reduce ice. Sometimes they can get rid of it for a period of time. But there will be some point in history in a very cold climate where the mixer gets overcome and you'll get some ice formation. Now this, in contrast with the tank next to it, you've got this large ice ring. These are all the shavings from that plug coming up and down. Is a drastic difference, especially on a bolted tank. But the real pertinent part is what happens in the spring or as soon as you hit a warmer weather period. In a tank that doesn't have a mixer, if you had ice in there in the beginning of winter and all through winter, it's in there all through spring until it gets warm enough to melt. That whole time it can be causing damage. Something that has a mixer in it, you can eliminate it faster and reduce the amount of time that damage could possibly take place. This is another freezing case study. This is Laramie, Wyoming. Another pretty cold place. And they had kind of the same situation. It's a 300,000 gallon pen, and every year they had ice in it. Every year. And they also had low turnover. Low turnover, in combination with cold temperatures, makes for very, very icy conditions. So we put the little mixer inside it, and you can see the difference between the two. This is the original picture, and then 4 days after punching a hole through it and getting the mixer in. So now they know that they have viable water in their water storage tank. Now what does inadequate mixing look like? Well, that's a good question. Not all mixing is the same, and like I said, you have to know what your goal is so you can prescribe the right technology, right size technology. 4 million gallon storage tanks, pretty common in the West. We hoard our water out there like it's going out of style. In this particular scenario, we were able to study 2 tanks side by side, running off the same system, same operational everything, 2 different technologies. In an ideally mixed situation, perfectly mixed, this is what the temperature string should look like, because we have 4 probes, 5 probes in here, different colors, and it goes up and down because those go with demand. Cold water comes in, water temperature lowers, and then it starts to warm back up, and then cold water comes back in. So this was with a mixer, I should say. This is what it looked like. And it's almost identical to that wave thing. The reason that these are off just a little bit, if you look at the scale, 14, 15, 16 degrees Celsius, then there's a margin of error on temperature probes, so on and so forth. But nonetheless, we know that a good spec says within 0.2 degrees Celsius. That's about as low down and as accurate as a measurement you can get with technology. This is the other mixer that was promised to do 4 million gallons. Oh, no problem, our CFD says it works. Well, you can distinctly see a difference between all the temperatures in the top. In other words, the large volume of water in it is warm, and then the cold water is just bouncing along the bottom. And then here's the last one of I guess you could call a failure. This is an interesting study in Southern California. The operator said, okay, there's all these technologies out there. I want to get 2 of them and see which one does better. And they set up their own test, and they did it all on their own. So for this particular test, it's not just temperature that we're studying. Temperature is one thing. Residual is the goal, though. Temperature is just easy for us to study. Well, this municipality said, I'm going to study residual. So what they did is they isolated the tank. All right? The tank was not in use at the time. It was full, but not in use. So they superchlorinated the tank. And then they shut it off, and they let all the chlorine settle to the bottom of the tank, because it's more dense. If you don't move it around, then it'll just settle. Okay? Then they have all these little sample points on the top of the tank. Those used to be cathodic protection ports. They took the cathodic protection out. Within the tank, they said we're going to sample at 3 different levels in the tank, and we're going to do it at 4 different locations. And we're going to do it multiple times a day over the course of 24 hours. So you can see what their goal is to make sure that the residual inside the tank, while being mixed, is uniform everywhere. In an ideal world, this is what it would look like. Perfectly uniform and slowly starting to drop off because there's no additional chlorine coming in. So you're going to start using some of it up. So this is mixer A. This is what it's supposed to look like. After 8 hours, get down here, 24 hours later, well within a performance specification, taking it from a steady state, blend the whole tank, and make all of the samples uniform for residual, right? I mean, it's pretty straightforward. Oops. Hey, oh, it's gone. Dang it. Well, there was another slide that was in here that showed another technology, and it looked like this for 36 hours. And at that point, the municipality said, you know what, if you can't mix something within 36 hours, then you're not going to be able to mix it when we start actually adding chlorine in here and operating the system the way we should be. So, in summary, stratification can happen anywhere. It's not just a warm season, warm place kind of phenomenon. It happens up here in Minnesota, it happens in Wisconsin, it happens up in Canada and BC, it happens everywhere. One thing to look for in terms of your systems to know that something is amiss, and it's probably happening in your storage system, look for residual drops, nitrification, or if you get a taste and odor complaint, even if it's seasonal, like in the fall. We talked about ice. Obviously, it's a liability. It's tearing up your coatings, and you pay a lot of money for that. And it can also cause liabilities in terms of failure of your tank. And then mixing can help. It's not a silver bullet. It is not the end-all, be-all. There are some tanks that don't need mixers. That's okay too. But what you can do with mixers is you can mitigate ice damage. Like I said, you can't eliminate it. You reduce water age, which is a big one, and ensure accurate samples. That's really important. Any questions? Yep.
Have you ever run into, especially a year like this year, you're now sending colder water down into those mains? Seeing any issues from that?
Sure. So the question is, have we ever seen sending colder water down into the mains if we're mixing, you mean?
Right, because you don't have that warm water sitting there just going.
No. And here's the thing. I mean, yeah, we are sending cooler water down into mains, but the water that we're sending to mains is never below freezing. So we can't send water below freezing down into mains because it'll turn to ice before we can get it there. So we've never seen in our history of 7 years any issue pushing colder water down into mains.
I like your chart showing, since it was moving water, that it was actually below freezing.
It can be, but we haven't ever seen like an issue. I mean, to have it be below freezing, it would be so nominally below freezing that I don't think it would cause an issue. We just haven't seen it. It's a good question though. Yeah.
I've got a quick one
Life
before we
expectancy.
let anybody go here. I need Charlie from Alden. If Charlie from Alden is in here, got an important note for him. No Charlie? Okay. Go ahead. Somebody?
So the question was life expectancy. It depends on the unit. We make multiple different units and so forth, and it's a tricky question when we talk about life expectancy. We took our tripod PWM 400 whatever mixer from a 2-year warranty to a 5-year warranty. Reason being, we got enough data from mixers in the field and wear characteristics that we could say, okay, we've had 0.5% failure rate on this. We can afford to increase the warranty. So every unit that we get out of the field, where we actively go into the field and buy them back from customers in exchange for the latest and greatest, we use those to to look at the wear characteristics. So life expectancy is difficult. Like I say, we've had such a small amount of failures, 0.5% of total fleet failures, and we've got about 1,300 units in the field now. Our hope is 15, 20 years. The simplicity of the design and everything being stainless steel, there's only one moving part, and nothing's constricted. And that's a big, important part of using pumps and using motors, is letting them operate efficiently. So I wish I had an exact answer for you, but I don't, because we're still trying to get as much information as we can. Yep?
Why doesn't more of that warm water go into the tank rise to the top?
Because at a certain temperature, so the question was, why doesn't more warm water that comes into the tank at the base, because heat rises, why doesn't it come to the top of the tank? And the reason is that at a certain cold water temperature, there's actually a change in density. Yeah, there's temperature inversion. But the cold water, the warm water at the bottom actually becomes more dense than the coldest of cold water right before hitting freezing. Any other questions?
Anybody else? Pretty interesting stuff, huh?
All right.
I've been in this business 40 years and you never thought about it until the last, I don't know how many years, but that water stays in there a lot longer than you think. So, very good job, Nate. Give him a round of applause.
Thanks, guys.